When we test for differences between means, what do the t-tests test? An independent t-test tests if the differences between the means of two groups is greater than would be expected by chance. Because we always expect there'll be some difference between groups, right? If we went and we measured the IQ of, say, 10 women in Santa Monica and 10 women in Inglewood, we wouldn't expect that their mean IQs would be exactly the same, even if in the population they really were exactly the same. So when we test for the difference between groups, the probability that a difference occurs just by chance, just by random error, is a factor of three things. First of all, the size of the difference between means. So if we found a difference of, say, 1 point between the IQ of women in Santa Monica and women in Inglewood, we probably would not be surprised. We might think that could occur just by chance. If we found a difference of 20 points, we might think, probably not. A second thing that makes it more or less likely that the difference we observe could happen by chance is the variance in the population. So we might not be surprised to see a difference of 1 in IQ between the population of Santa Monica and Inglewood, but we'd be very surprised to see a difference of 1 in the mean number of limbs, because the mean number of limbs people have generally tends to be 4 with very little variance. The third thing that is related to the probability the difference might occur by chance is the number of people in each group. And even if you're not a big statistician, you probably realize this kind of just inherently, that if you find that 2 people you measured in Santa Monica have a slightly higher or lower IQ than the 2 people you measured in Inglewood, it doesn't mean that much to you. Even if there's a big difference, it doesn't mean that much to you because there are only 2 people. But if it was 20,000 people, then you might not think those differences would occur by chance. So that's kind of the basics of the idea behind probability and looking at the differences between means. Now, what if you have more than 2 groups? Do not do a bunch of t-tests. I mean it. The probability less than 0.05, the p less than 0.05 that we use to accept or reject the null hypothesis, means a result would occur by chance 5 times out of 100. If you do 20 t-tests, you'd expect 1 of them to be significant just randomly. If you do 100 t-tests, you'd expect 5 of them to be significant just randomly. So do not do a bunch of t-tests. So then what do you do? Well, one-way analysis of variance. So let's take a brief review of that. The ANOVA tests mean differences if your question is, are the means of these 2 or more groups different? If you only have 2 groups, you could do a t-test, get the same results. Your answer in this case is probably ANOVA. If you have more than 2 groups, you need to do an ANOVA. If you only have 2, you could use a t-test or an ANOVA, whatever makes you happy. ANOVA answers this question. Is the variance among group means greater than would be expected by chance given the variance in the population? In explaining variance, remember, variance is the sum of the squared difference from the mean of every observation divided by the number of observations. That's all the variance is. And the square root of the variance is the standard deviation, which is just a fact and kind of irrelevant for this point. ANOVA assumes that variance consists of 2 parts. Variance explained by the model, that is, group membership, and variance not explained by the model, or error variance. Now in that case, we don't really mean it was error in the sense of being recorded incorrectly or that, but it's just variance that cannot be explained by your model, say what city you live in or what your gender is. So let's take an example of this. Here we have 2 variables. We have insecure, which is the mean of items on a scale of bullying, sexual harassment, racial ethnic tension, and disorder in classrooms. So the higher score it is, actually, the more secure you are. So 5 on all of these, say, would be it never happens. And then we have this FR level, which is the level of the school. So elementary school's a 1, middle school's a 2, and high school's a 3. So we have 3 groups, and we have a variable that's continuous. So we're going to do a one-way analysis of variance, answering the question, what makes children feel insecure at school? No, this is not an example of racial problems. That's actually my daughter and her friend goofing off. So here's some output from SAS. It tells us that our dependent variable is insecure, their score on that measure. And the model has 2 degrees of freedom. The degrees of freedom are always going to be 1 less than the number of groups. And the sum of squares explained by the model is about 82, 81.9. The sum of squares error is 944, and the total sum of squares is going to be the sum of that. Now, here's kind of an important thing. It tells us that the R square, the proportion of variance explained by our model, is about 8%. Kind of makes sense up here, right? 81 out of 1,000, about 8%. So which category of school you're in, elementary, middle, or high school, explains about 8% of the variance in your score on how insecure you feel at school. Over here, we get an F value. F is similar to a t-value, and it says how likely is this difference among means to occur by chance if your null hypothesis, and your null hypothesis is that all the means are equal, if your null hypothesis is in fact true. You have an F value of 106, and the probability of a value that high is less than 0.0001. So you would reject your null hypothesis. So you would reject your null hypothesis and say there does seem to be a difference among the means, more than would be expected by chance. And just in case you want to know, the group mean for the entire group, all 3 of them put together, is 3.88. Now, in this case, we only have one variable, which is the level of school they're at, if it's middle school, elementary, or high school. So you could see that the model sum of squares is equal to the sum of squares explained by this particular variable. Now, if we'd had 3 or 4 variables, that wouldn't necessarily be the case. But here we only have one variable, level of school, and that's the variable explaining the explained variance in the model. So we reject the null hypothesis, but what is the null? The null is that the mean of group 1 equals the mean of group 2 equals the mean of group 3. Now, it could be that group 2 is larger than both groups 1 of 3, and that's perfectly okay with ANOVA because it doesn't assume a linear relationship. It just is treating every group like a different category. And those groups could just as easily have names instead of numbers. Now, we've rejected the null hypothesis. There is no difference between any of the means. Now we want to know which means are different from which other means. Elementary schools can be different, but high schools and middle schools are pretty much the same as one another. So the post hoc tests tell us which means are different. You don't need to do this when you do an independent t-test because you only have 2 groups, and so the 2 are different from each other. Now, one really useful thing that SAS does is it will do a plot of your means. So here we see that children are most secure when they're in elementary school. This is actually the mean, and this is the confidence limits. They're most secure in elementary school. It drops in middle school, and then it goes up again in high school. I love plots. Here's the code. procGLM, data equals the dataset name, class, so this would be any categorical variables. If you're doing an ANOVA, you need at least one categorical variable. Model, the dependent variable, equals the independent variable. Means, the independence that you want the test for, slash, and then the post hoc test you want. So that's the syntax. Here's an example. procGLM, data equals mydata.boolean, class, fr underscore level. That was what our independent variable was. Model insecure, our dependent, equals fr level. Means fr level slash Tukey. The Tukey test compares each of the means with each other. So it does pairs, 1 to 2, 2 to 3, 1 to 3. And that's a pretty common thing that people would want.